And now, speaking of work, we're happy to turn to our guest segment. And to introduce that, we're going to take a look at a trailer for her latest work that was all over the internet. Take a look here. Ladies and gentlemen, we're super pleased tonight to have with us Dr. Michelle Collins from Surrey. Now, is that Surrey University in the UK? What?
It's the University of Surrey, yeah.
University of Surrey. Well, how exciting is this? Now, you're currently there you're in Surrey right at the moment. You didn't fly to LA during all this COVID, did you?
I did not know. That's expressly forbidden at the moment. We're not allowed to travel outside, really, our own towns at the moment.
Most places,
Trip to LA would be.
Yeah, Americans can't go anywhere either in general. So
yeah, good. Well, then we're breaking no rules.
Breaking no rules. Well, thank you so much for joining us virtually, shall we say, over the internet. Now, we played the promo video that you made about your new paper. So, yes. What is a little bit of the story behind that, if you can? and also, what do you do at university there? You're an astronomer, I know, and you've been doing research, but you also teach. Tell us a bit about yourself.
Yeah, so I've been at the University of Surrey now for almost 6 years. And I started, it's my first permanent academic job, hopefully my last as well, if everything goes well. So I started as a lecturer back in 2015. I was recently promoted to senior lecturer, which is, so we have a very different scale here where I think in the US, I would be considered a professor by now, but for us, you have to really age to about 70 to be a professor or something, it seems like. So, but I'm at sort of an equivalent level here in Surrey. So I'm an astronomer there. So I work in a physics department, and my job is part teaching for the undergraduates, and then also research, both through my own research and also with PhD students and postdocs as well.
Mm. Well, awesome. Fantastic. So now, what is the story behind the promo we saw in the video? It's quite fantastic. It made a lot of folks on Twitter excited, I know, and I thought that we need to have Dr. come on as a guest. So, and by the way, I like to, here at Griffith University, here at Griffith Observatory, we do actually like to use our honorifics like doctor to show off the hard work you did to get in this position. I know our own director, Dr. Kropp, likes to do that, so I'm going to honor you that way. But of course, I've known you for a little while, but I didn't know you were so talented at making these promo videos. So what happened with this one?
Yeah, so it was actually just a bit of a throwaway kind of fun thing I did. I've been working on this particular paper was something I started back when I was working in Heidelberg in Germany in 2013, 2014. I got some really exciting data in, and I started writing a paper back then. And it was kind of almost in a stage where we could think about publishing it. But then I moved to the US for a new job. And I was just there for 1 year before I moved again to the University of Surrey. And so it was just a very kind of turbulent time where I was getting used to new places, starting new projects and new collaborations. And this paper was just kind of always simmering along, in the background, something I would keep going back to and not quite getting done. And then, of course, the longer these things drag on for, the guiltier you feel about it. So, the less likely you are to want to open it up and see what you last wrote 3 months ago when you thought about last thought about doing anything with it.
So did any of your colleagues, any of your co-authors on the paper, were they pressuring you to get this done? And did you keep any emails from them unopened for months at a
No,
time?
it was sort of the other way around. I think the last stage I had, I'd sort of like pushed the ball back into a couple of people's court to do some modeling. So I'd got the observations, I'd done the analysis, and we'd done some like preliminary models of the data. But we were thinking about what the next step was, and that was not really my territory. So that was where we left it. And so luckily, I was not the last person left with an action item. And actually coming to the University of Surrey was great because my colleague Justin Reed is actually super good at this modeling stuff. So we started talking about it, and he was like, oh, my tool will work great for doing the model of this galaxy, this little galaxy. And we can learn about if its dark matter is really lower density than we expect, which was the exciting thing about the object in the first place, is that it seemed to be lower mass than we thought it should be. So then he was able to help me do the modeling. Well, he did the modeling, and like he joined the paper, joined the team. And in the end, like that 7-year delay, I think totally made it a much better paper than it would have been had I published it in 2014. But, it felt like this massive journey and a thing that I'd been just like in the back of my mind for so long. So when I submitted it, I was like, well, great, now it's submitted. I want to do like a little celebration. And I'd seen that iMovie has these little movie trailers you can make. And I was like, I wonder if I can make a movie trailer for my paper. And it turns out it's super easy to do. Like you just give it a bunch of images and like write a couple of captions, and it does everything else for you. So I just took a bunch of screenshots, some of them serious, some of them less serious. Like my favorite one is where the appendix scrolls across. It's like one of the least interesting parts of the paper, but it has its own special like swipe. And so I made it, and I was just, I thought it was hilarious, but I often think things I do in lockdown are really funny, and, and not everyone else gets it. So when I was done, I just put it on Twitter, and I expected to get like a handful of, of likes. And it just kind of blew up. So my Twitter was like just endless notifications of people really enjoying it and really appreciating it. So it ended up being far bigger than I had envisioned. And a few other people have started making trailers since. So I worry that I've created a thing that we'll all have to do every time we publish a paper now.
I fear you have done that, and I also fear that now, before every talk and colloquium, we'll have to watch 10, 15 minutes of trailers of future papers.
Yep, yeah, it's going to be just like a trip to the cinema. Yeah, we'll also start selling really expensive like snacks to bring in a bit of extra travel money.
If you want that Mars bar, then you're going to have to pony up the cash. And that joke works both across there and here, by the way, but don't expect to be the same candy bar if you ever travel here.
Yes, no, I've experienced that. It's very different.
Yeah. Anyway, back to the paper. You study I did. I still do a little bit here and there. I dabble, but you're still deeply involved in research in the local group, and both of us love the Andromeda system of galaxies and Andromeda itself. I know it's dear to my heart as well. It's my thesis galaxy, as you know.
Yes.
But you have studied a whole bunch of the dwarf galaxies around Andromeda. And how many of them are there now? And which was the target of your most recent paper?
Yeah, so I think in total, there are 35 dwarf galaxies, of which I think 31 are dwarf spheroidal galaxies, which is the type I study. And those are the smallest galaxies we're able to find in the universe. So the faintest, the lowest mass. And they're also super interesting because they seem to have really high dark matter ratios. So compared to like a Milky Way or an Andromeda galaxy, which has, some fraction of dark matter, they seem to be much more rich in dark matter with many fewer stars. So that's why we're really interested in studying them, because they can maybe tell us more about what dark matter is and how it behaves. And the dwarf galaxy I was studying in this case is known as a very catchy name, as most of them are. And this one is Andromeda 21. So I think I'm one of the few people, maybe of only like 2 or 3 people in the world that is intimately like acquainted with every single dwarf galaxy in Andromeda. So if someone says Andromeda 23, I'm like, oh yeah, I know that guy. But no one else does. But Andromeda 21 is one of my favorites. I have about 3 favorites. And it was super interesting, like I say, because while these systems are supposed to have a lot of dark matter, this one was coming up from our initial studies back in 2011 and 12. A seemingly lower mass than we would expect, but we only had a handful of stars to study it with, to get a mass measurement from. And that wasn't really enough. So we went back and re-observed it to get more stars with more velocity measurements. And then you can use those velocities to kind of figure out how much stuff there is in the galaxy. And it still comes up as surprisingly low mass, which is a really interesting finding. And then we have to
Now,
try and understand what that means.
now what is low mass for a galaxy? For
Uh,
one of these
so
dwarf spheroidals?
Yeah, so a galaxy like the Milky Way has something like a total mass of around 10 to the 12 solar masses when you combine its stars and its dark matter. So that's like, a 1 with 12 zeros afterwards. The types of dwarf galaxies that I study are far lower in mass. So their total masses are probably more like 1 times 10 to the 9. So like a factor of 1,000, like lower mass in total. But then if you compare the number of stars, it's more like they have, I guess, 7 orders of magnitude fewer, the ones I'm studying, than the Milky Way. So much less bright. And some of the galaxies we find that are dwarf spheroidals are, fainter than a single giant star. They have so few stars that if you look at an image of them, you'd think you were just looking at an image of empty sky. But to the keen-eyed astronomer, you can see a couple of little dots of light that make up the dwarf galaxy. So they're really, really faint compared to the normal images of galaxies that we tend to see.
Interesting. Now, what goes in to getting a mass? You were saying getting velocities for the stars. So what instruments do you use regularly to, first of all, to see the stars, to know where to point telescopes, and then how do you get their velocities?
Yeah, so I'm working or have worked extensively as part of a team called the PANDAS team, which is the Pan Andromeda Archaeological Survey team. And we used mainly 2 telescopes to study Andromeda. So the first one is to take images of Andromeda and its outskirts, so very far away from the disk of the galaxy and out into its outer stellar halo, as we call it. And the telescope we use to do that imaging survey is the Canada, France, Hawaii telescope, which is a 4-meter telescope on the summit of Mauna Kea in Hawaii. And so from that survey data, from that imaging, we can go and look for these little dwarf galaxies that orbit around Andromeda. And once we found them, we then moved to a larger telescope. So we use the Keck telescopes on top of Mauna Kea, which are 10-meter telescopes. And we use typically the Dmos Spectrograph, which is the Deep Extragalactic Imaging Multi-Object Spectrograph, I think. It's been so long since I've had to say the acronym.
Not bad.
And that allows us to take, with a single pointing, you can get, you basically take a lot of slits that you put into a big aluminium mask, and each of those slits will cover the position of a star. The light comes through to a spectrograph, gets kind of spread out, so you can then measure wavelengths of individual absorption features. And we know where they should be if those stars were at rest, but they're all shifted. So we can then figure out how fast the star is moving from how much those lines have shifted away from what they would be if the stars were completely still. And then we can use those velocities and the positions of the stars, and then, just simple gravitational laws to understand, how much mass there must be contained within a system based purely on how fast the stars are moving. So if there's not a lot of mass, the stars won't move very fast. And if there's a lot of mass, they'll move a little bit faster. So we just tend to we look at what the random motions of the stars in the galaxy are, and use that to work out what the enclosed mass must be of a system. And then we compare that to what we expect the masses of these systems to be when we consider just, normal, the lambda cold dark matter cosmology that we use in astronomy.
How is it that you can use velocity to tell the Andromeda stars in these dwarfs from the Milky Way ones? What's the giveaway?
So we basically know what the stars. So M31 is currently moving towards us at a relatively fast speed. And so it's quite removed. If you look at how the M31 galaxy is traveling towards us, and then how stars in our own galaxy are moving, they have very different velocities. So you can then assume that M31-like stars will typically be closer in velocity to M31 than they will be the Milky Way. So then you can very easily often see that you'll have, Milky Way-like stars on one side of your graph, and then like a big booming peak of stars with a very narrow width in velocity that is your M31 dwarf galaxy. Now, that's not always the case, but it was the case for Andromeda 21. We have some dwarf galaxies that are very inconvenient, where they have a velocity that is offset from M31 and much more similar to the Milky Way. And this causes us many headaches. But we then have to just be a bit cleverer about how we assign probability to a star being part of the dwarf galaxy versus the Milky Way.
Interesting. So now this Andromeda 2023, you said?
21.
Yeah, not 23.
No,
It's 21.
23. No, forget
Yeah.
23.
Yeah.
That's not interesting
They
at
get
all.
each other's mail all the time.
Yeah, exactly. Same side of the street. Now, Andromeda 21, is it the least massive Andromeda dwarf you've come across?
So it's not the least massive, it's just seemingly lower density than you would expect or lower mass than you would expect for the number of stars it has. So it's a reasonably bright, for a dwarf spheroidal galaxy, member of the Andromeda 21, the Andromeda system. So it has, quite a few stars. And in general, as a rule of thumb, you expect that the more stars a galaxy has, the heavier its total mass is, because the more mass you have in a galaxy, the more gas you can hold on to, the more stars you can form, the brighter your galaxy becomes. So, more mass means more stars. And you can actually make quite a good relationship between the total mass of a galaxy and the amount of light it has. So then we can kind of say, this galaxy looks as we would expect. This galaxy looks maybe slightly more massive, slightly less massive. But Andromeda 21 is sort of significantly less massive than we would expect based on the number of stars it has. And so that's why we were quite interested in it, because it's hard to explain without invoking additional physics beyond maybe what the standard expectations are for the galaxy.
Do we have an idea of the age and metallicity, the chemical content for our audience out there? How do they compare to the other ones? Is it unusual in any other way?
No, as far as we can tell, not. So in terms of the metallicity and the ages of the stars, they all look very old and reasonably metal poor. And in fact, in that case, it looks very consistent with what we'd expect for a system with that many stars. So the metallicity looks right on where it should be. So the chemical composition is right. The ages look right. One area that it does differ a little bit is it's also slightly more diffuse than we would expect. So a little bit more, its stars are a bit more spread out than a galaxy of a similar luminosity in the Milky Way would be. So almost as if it's kind of expanded away from the norm. So that's maybe a hint into what's happening there, that it has this more diffuse population of stars.
Is there anything in its neighborhood at all? Anything it could have interacted with that could explain this? I mean, obviously, I know there's a big nasty spiral next door. I get that. But how close is 21 to 23 and other things it might have interfered with?
Yeah, so it's pretty isolated, actually. Well, it's still around Andromeda, as you mentioned. So, but otherwise, there's nothing else really in its immediate vicinity that it's likely to have interacted with. Now, we don't know exactly where it's been in the past, and that's quite interesting, because you have this is a good explanation for what we're seeing here, is though the galaxy is currently pretty far from Andromeda, it's very possible that if it has quite an extreme orbit that brings it close, then over time, as it comes past Andromeda, it can get tidally shocked, which means the stars kind of can be compressed and then expand. The dark matter content will do the same. You might strip some of the dark matter off as well in these interactions.
Yes.
And then by the time it moves back out to the outskirts of the halo where it is now, it kind of will expand and just appear like lower density in terms of its stellar component, but also in terms of its dark matter component. And that could be why we measure a lower mass than we expect now. And so that is a good possibility for what could happen there. But it does mean it would probably have to be on quite an extreme orbit.
Yeah.
And unfortunately, because we can only measure how the object is moving with respect sort of along the line of sight. So we only have one component of the motion. We don't know where it's been moving in the past. So if you have 3 dimensions of velocity, like you can measure for some of the Milky Way dwarf galaxies, you can work out what orbit something's on. And then if it's interacted with something massive in the past, or one of the smaller galaxies had a flyby with it in the past. You could try and map that out. But for Andromeda at the moment, we can't really test that. But it is a good method. It is what you would expect to see if it had an interaction in the past.
Right.
In rare cases, they'll leave streams behind, and you could just trace out where the orbit is. It's a visual indicator.
Well, yeah, like the LMC and the SMC.
Yeah.
We're not so
that
lucky.
Means it has to be right at the end of its lifetime. So by that point, almost all the dark matter's gone. You've stripped the majority of material, and then finally the stars get peeled off into these impressive streams. So if Andromeda 21, though, is in an earlier part of its destruction, then you might not see any of the stars leaving yet, but a lot of its dark matter could already be gone. And that makes it really hard to tell whether or not a dwarf galaxy has been tidally affected. So they may look completely normal, but actually much of their dark matter halo has been gone, just because that's often what goes first.
Mhm.
And it makes it very difficult for us.
So, now, is there an Andromeda dwarf that happens to have a lot of dark matter that's on the other end of the spectrum that's dark matter rich? So the stars are flying around faster than you'd expect them to be.
No, we do have some interesting dwarf galaxies. So there's like the compact elliptical galaxy M32,
Right.
which is very dense in terms of its stellar component. And I think there it's hard to tell what's going on with the dark matter. But that's a super interesting system where the stars are so tightly packed and it's so massive that it's kind of hard to understand how that galaxy has evolved. And some people have recently written a paper that suggests that it's actually sort of the nucleus of a much more massive galaxy that kind of came into Andromeda in the past and has been like all the outskirts are gone and now in a beautiful stream that kind of arcs around the whole of M31. And that's just kind of what's left over. We don't know if that's the case, but that galaxy is super interesting because it does appear really dense, but it's really hard to disentangle because the stars are so dense. We don't know if it's just dense in stellar like component or if it's really an outlier in dark matter too. I think that's the case. I know a little bit less about that galaxy, but it's certainly very interesting and very much the opposite of what we see for Andromeda 21.
32 is pretty close to the disk, is it not? I
It
mean,
is.
it seems visually to be, but I believe it actually is. I mean, they've got a Tesco and everything. They're right downtown. So, sorry, Breton joke there. Does it seem to have been highly modified, or it's just so strange we really don't know what its story is?
Yeah, it's because what we see now is just sort of almost a perfect sphere, I think, for M32. So it's a really compact ball of stars. So it could be that it had this outer component that's now been completely removed, and that maybe is what makes up what we call the giant stream. But in terms of what we see now, it's just very hard to say. And again, as it's so close to M31 as well, I think it'd be hard to see if there was any kind of remnant sort of stripped population still hanging around the outskirts. So really what you can just see is that very dense central part, I think, is what's happening there.
Do you agree that globulars seem to be thoroughly stripped down former galaxies, or they're
I think
their own
some
beast?
fraction of them probably are. So some of them will be little nuclear clusters that are left over. But I think many of them are star clusters in their own right. So probably not stripped galaxies for the vast majority of them, I think. I think that's the generally accepted view at the moment. But some of them certainly, like these unusual things like Omega Cen in the Milky Way, is I think the poster child for this kind of weird behavior. And seemingly that was maybe brought in originally as part of a massive galaxy that's now been stripped down.
Yeah, that's where my question of multiple stellar populations goes. In Omega Cen, there's clear evidence of different colored red giant branches, and they would span sort of a range of colors. Changing the subject ever so slightly on this, what do you think is our best chance of learning what dark matter may be comprised of? Do you have a favorite program that's investigating that? Do you have what would your money be on if you were in Vegas?
I think some of the interesting stuff that's going on right now, there's sort of two avenues that I think are quite promising. In addition to obviously studying dwarf galaxies, which are super interesting and have been providing some constraints, but we do now know that the stars mess up a lot of our what we thought would be the easy ways of getting at the issue of dark matter. But for example, one of my colleagues at the University of Surrey, Dennis Erkel, he works on stream structures. So when either globular clusters or dwarf galaxies are interacting with a massive galaxy like the Milky Way, some of them will get destroyed and like they get their stars pulled into these beautiful streams that can loop all around the sky. And those that are made from things like globular clusters are really interesting because they tend to form these really thin, kind of pristine looking streams. And what we expect from dark matter is that the Milky Way halo is full, if it's cold dark matter that we have, which is the current paradigm. There's all of these like empty dark matter halos that just have dark matter, no stars, no gas, and they're quite low mass, just floating around all through the halo. Now, if one of those punches through, like comes into contact with a globular cluster stream, it'll punch through and it can make a little gap that forms in the stream. And these gaps then, if you find them, can show you that something must have passed through the stream. And if you can show that was a dark matter subhalo, you can start to say, okay, well, we know that dark matter substructure exists in the Milky Way, because of these gaps in these streams. And you can begin to constrain then what the mass of these invisible dark matter structures are. And that just really is something that then you can't explain using other physics like modified gravity or something like that, if you can show that they are formed by subpolar halos. Now, that is quite hard to do, but there are a lot of very smart people working on it. So I think that they can begin to, start to either confirm that something has to exist or rule out certain masses of subhalos using these beautiful streams with these gaps in. But it is very difficult to do. But that's really exciting, I think. I think it can make really competitive constraints and a really great argument for the case of dark matter.
Fantastic. That's very interesting. Now, let's see here. What else? Patrick, do you have any questions you've been wanting to ask?
I was wondering if you've studied dwarf galaxies of our own Milky Way, and and maybe possibly other nearby galaxies.
I have dabbled a little bit in the Milky Way, yes, but largely I've focused on M31. But my PhD students worked on the Hercules dwarf galaxy, which is this interesting dwarf galaxy around the Milky Way, which appears to be much more elongated than most Milky Way dwarf galaxies. So there's a long-standing argument as to whether or not it's a dwarf galaxy that's in the process of being pulled apart. So then that's why it's kind of longer on the sky. And so she did a study to see how likely that was by comparing it to some models of what you would expect if it was being pulled apart. So we worked on that for a little bit. And then I've been involved in some Milky Way stuff as a co-author, but at a bit of a lower level. There's Triangulum 2 as well, which is a cool little dwarf galaxy that I worked on with Nicolas Martin. But yeah, just a few things in the Milky Way. And then also the Tucana dwarf galaxy, which is an isolated dwarf galaxy, which seems to be quite dense in terms of its dark matter content. So that one's a bit of higher mass than we would expect. And then I've just recently got involved in some imaging surveys where we're searching for faint dwarf galaxies around dwarf galaxies that are sort of more isolated and further away from the Milky Way, as another way of trying to learn about how these faint systems form and the different sort of physics that governs how they evolve.
I suppose it makes sense that you'd have co-orbiting dwarfs, but I just never heard of an example before. I'm not very cosmopolitan in my outlook. There really are known examples of dwarfs going around. Okay, all right. My world is enlarged, but that's what these shows are for.
So one good example is it's a sort of a higher mass dwarf, but the Large Magellanic Cloud has a number of dwarf galaxies now that we know orbit it. So SMC is one, they're a little bound pair, but also it has a number of very faint dwarf galaxies that we think now fell in with the Large Magellanic Cloud, so that that's like a bunch of dwarfs orbiting a dwarf. But then there's also some other examples. I think that I worked on a paper with Mike Rich on NGC 4449, which is a star-bursting dwarf galaxy. Right. And in its outskirts is like another smaller dwarf that's being sort of pulled apart as it orbits around. So that was a nice little dwarf orbiting a dwarf. And it was found actually at the same time by two different groups. So that was really cool as well.
Yeah, I'm on that Nature paper with you.
Yes, there you go.
That's one of the work I still dabble in now and then. So I was involved in that study. And indeed, we were some of the first folks to find a dwarf galaxy around another little dwarf, and it made it into Nature, which was great fun. And I think that is the most recent paper we were on together. That was in 2012. So yeah, good times. Yeah. So thank you for bringing that up. I didn't have to. I was going to. You and Michelle brought it up on your own. So how exciting. Gosh, what do you have that's your most current exciting target to go observe? Now, don't give away any research, of course, secrets you have, but if you have telescope time coming up, do you have any observing plans that you're excited?
No, I mean, we do have something exciting that's coming out soon, but I don't think I can talk about it yet.
Well, maybe you'll have to
you could release a trailer, though.
Well, maybe
like
I will.
A teaser trailer.
Yeah.
But yeah, there's a cool little thing. I've been working with David Martinez Delgado on a really exciting project, actually. So that's coming out soon, and it's actually been mostly my PhD students that have been working on it, and which is nice as well, but I've been helping, as a good supervisor does. So that's a really exciting thing that's, in my opinion, that's coming out quite soon that I can't tell you about. And otherwise, one of my PhD students, Norshin Karim, is working on a survey of the halos of some isolated dwarf galaxies to look for these dwarfs of dwarfs, but also any evidence that they have maybe some stream features in their outskirts. And we're quite excited about a couple of things that we're seeing there, that we have to do a bit more statistics to see if they're actually real or if we're just squinting at blobs, which is unfortunately a lot of what I do these days. But yeah, so there's some very exciting work on trying to see how common dwarfs around dwarfs are. And we also think they might be interesting if you find them, because they'll be very faint systems that live around reasonably low mass galaxies. So they may have very different properties from the dwarf galaxies we see orbiting the Milky Way and Andromeda, just because they're living in a much less hostile environment. And much of what we know about very faint galaxies, we've learned from our immediate surroundings. So if we can find them in different environments, that's a really exciting thing in terms of learning more about these really interesting systems.
When you describe the environment as hostile, do you mean hostile to it continuing as one large blob? Gravitationally hostile, I presume. Okay.
Exactly, yeah.
Well, you never know what's going on out there, really.
Yeah, I mean, who knows? But yeah, I think if you're living in the halo of the Milky Way and you get too close as a little dwarf galaxy, it can be quite bad for your continued survival. I mean, we see this with the Sagittarius dwarf galaxy. I mean, that was quite a big galaxy, and it's not faring so well these days.
No,
not at all.
Very sad.
Yeah. Now, a question that I got asked more when I went observing was, what was the weirdest thing that ever happened observing to me? Now, they always wanted tales of UFOs and aliens, and I had to tell them, no, actually, astronomers generally don't see UFOs and aliens. Maybe it's that we're familiar of what things are up in the night sky and know what to expect and can explain away much of what people think might be there. However, have you ever seen anything weird or had anything fun happen while observing, something unexpected?
So I've not seen anything weird, but I did have an observing trip a few years ago now with Nicolas Martin, and we'd gone to observe some Andromeda dwarf galaxies and streams at Keck. And when you go to use Keck, you don't actually go all the way up to the mountain, you just go to Waimea and you remotely observe from the bottom of the mountain, which is quite nice because you don't get any of the altitude effects. Right. And there's a bunch of restaurants next door, so you can have a nice dinner before you start. It's all very civilized. But this time when we went on this trip, it was kind of a case, we were doing half nights. So we were doing the second half of 2 nights. And the first half was being observed by another group. They were working on something entirely different to what we were doing. And so we arrived on the first day. We decided we'd go for a little drive around the island. And we went on this drive, and almost immediately we were on a road cutting across the island. And we saw this truck coming towards us with like a big bird cage on the back of it. It was kind of teetering around, and it just fell directly in front of our car and then bounced out of our path. And we were like, oh, close call. That's a bit strange. Carried on with our drive, and we got round to Hilo. And suddenly the rain came in, and it was really quite intense, and the roads were getting kind of slick. But then we got back to Waimea, and as we did, all the TVs turned on to warn about flash flooding where we'd just driven. So we're like, oh, that's another bullet dodge. That's pretty good. And then we went to the observing room at about 2:00 to just check the setup and everything. And we were told that the person who was observing ahead of us had been involved in a car crash, and they weren't sure if he'd be back in time to observe, and they weren't sure if they could set up a remote connection for his team. So would we be able to do the observations if they couldn't do it? And we were like, I don't know. But luckily he showed up. He wasn't too injured from his car crash. He did his own observations. But then we had like an amazing clear night. We had perfect like conditions. It was great. We went to bed, and the next morning we got up, and there was I don't know, half the island wide power cut. So there's no power anywhere. And we were told by the astronomers, like, if this continues, we're going to have to drive you up the mountain at 10 p.m. for you to do your observations, because there's just no way you can do it from here. So we had to like get up, so we'd gone to bed, obviously, like in the morning. And then we had to get up at 10 and just go and see what was the deal. And they said, no, we could stay. Like, it seemed like the power was going to be okay. And then we did our observations there. Again, like perfect conditions, despite the weather being pretty terrible just before we started. So again, another perfect night. And then we were about to go home a couple of days after that, and this huge storm system was going to come in. Like, it was the biggest storm system that was going to hit the island for like years. And we were getting all of these hurricane alerts as we drove to the airport, and like people were trying to buy our tickets to get off the island. And so we managed to get off the island. And then when we landed in Seattle for our like change, there was also all these forest fires. And so we got off and everyone was wearing smog masks. And it's probably the most eventful trip I've ever had, where we had 100% success getting our observations at the same time. So just like a really wild ride of near chaos.
I have no idea how dangerous astronomy was. This is reading much more like Indiana Jones hacking his way through the jungles to get to the observatory.
Exactly.
There was a period of time where astronomy was one of the most dangerous professions on Earth. And it was because there were very few astronomers, and things like they would get in car wrecks driving up the mountain, fall off the mountain going up, or coming
Mhm.
down in the morning, generally when you're tired, not so
Mhm.
much going up. Or, domes that rotate past things and people, anyway, horror stories. Very awful things have happened, but I'm glad you survived that night of observing, and I really appreciate you coming and sharing all these wonderful observing stories and the story behind that promo you made. We're going to have you back sometime when we're live again. Maybe you'll still be in England. We might do it remote, but we have no audience here to ask any questions. And normally they're pretty good and would pepper you with a few. So we'll bring you on back next time we're doing the show live. And next time you have a Keck run and a paper published to tell us all about, but we will expect a trailer. So just
Yeah, for everything. You've raised the bar. You
yeah.
really have.
I've made
And
everyone's
maybe
life.
action figures too. Yeah, we want a full campaign for this.
And everyone will know which one Andromeda 21 is. It'll be the one with the cool action figure. Yeah.
Absolutely.